Hello, welcome to a new episode of Mostly Engineering, and today we are going to talk about color. Welcome back to the channel, and finally it's some time again for YouTube and also some model building. And my first project will be this little Zero Fighter. And by doing the research, you come across a question, which colors to use. And this is usually a quite difficult decision, as also professionally this is a decision that takes quite a bit of time to find, and then sometimes it gets changed a lot mid the way. So not an easy one. And if you look at Japanese aircraft at the time, there is one corrosion protective color called Aotake. No idea if this is the right pronunciation, but it's this beautiful color over here. And there's quite a bit of discussion. Some say it should be much more green, it should be much more blue, it should be yada yada yada. And usually comments in the forums are helpful, giving you a lot of options, but there's also always this odd comic book guy type comment saying this is the right color, and if you use anything else you're not a modeler at all. And they're usually written with this I'm the expert, I know what the actual color is. And the question is, can we actually know what the color should be? And by my formal training and what I teach at university, I'm an engineer for printing and packaging technologies with a heavy focus on printing. And in printing, color accuracy is a big deal. Big enough that we spend a whole semester just on this topic. And the first thing that will surprise you with color accuracy is that color isn't a real thing. Color is not something that really exists. Color is a perception that our brain makes up when we see stuff with a specific re-emission spectrum. So how does it work? Physically speaking, color is our perception of a specific re-emission spectrum. So here on our x-axis we have our wavelengths in nanometers. So we start at 400 to 780, so roughly the area we can perceive as visible light. And on the short end we have our blues, then in the middle our greens, and over yellows we go to the reds on the long end. And here on our y-axis we have our intensity. And for a specific color we would have a specific re-emission spectrum, and for magenta that would look something like this. And very simplified to speak is everything above this line gets absorbed and everything below this line gets re-emitted. And so as magenta is this slightly bluish red, we see we have a little bit of emission in the blue areas and then a lot in the reds. But what we see here is the ideal version. This is how we would see the re-emission spectrum under ideal white light. So ideal white light is nothing, the emission spectrum would look like just a straight line, because every single wavelength is present with the same intensity. But as the term ideal suggests, this doesn't really exist in the real world. Daylight is relatively close, but if you are looking at a daylight spectrum, so something like this, and you see this is everything but a straight line. Now natural daylight is a little bit better, but it changes throughout the day depending on the weather and yada yada yada. And what we have here is a daylight after the standard D65, and we see we have a little bit in the blue missing, and then more or less here in the red. And please remember this value over here, because as color is a re-emission of light, it can only emit or re-emit wavelengths that are there in the first place. So if we are watching our magenta under daylight, the spectrum would look something like this. So we see the valley again, and compared to the ideal version, which we can lay on top, we see a little bit in the blue is missing, but not so much. But here in the reds, lots of emissions are missing. So for us, that would mean our magenta would shift a little bit more towards the blue. But daylight is not the only emission source we have. So if we look at incandescent light, for example, we would have this curve, basically nothing in the blues, and then a steady rise towards the yellows and the reds. And this is also why we perceive incandescent light as really nice and warm. And our magenta would look something like, yeah, you see the reds would emit perfectly, but the blues would break off more or less completely. So our magenta would shift much more towards the reds again. So, physically speaking, color is constantly changing. But if you go to the world, this is not our perspective, because our brain takes the light source into account and tries to even these differences out. What it does is basically exactly the same as our digital camera, and it applies automatic white balance. Just that our brain is a lot better in it. But a lot better doesn't mean perfect. And if we have to match colors, we see that this is the reason why this becomes hard. Because our brain gives us a little bit of false accuracy here. And if we really want to know if this shade of green is exactly the same as this shade of green, the only option we have is to put them right next to each other and preserve them, watch at them under the same lighting conditions. Otherwise, we can't really tell. And this is only the problem with perceiving the object with our own eye. Now, if we go back to our Zero or any other aircraft from the time, we usually don't have it at hand. So our reference are the instructions or photographs. And here we have the problem that, again, to the changing of the colors, we now put it on a photograph. And most of them are black and white, so for color reference, not really good. But color photos existed at the time. But again, this photochemical process changes the color. And here we have a picture of a Messerschmitt over Africa. And as you see, it changes the colors by quite a bit. More modern immersion got a lot better in color rendition. Our digital sensors today got a lot better in color rendition. But again, this process of taking a photograph changes the color a little bit. Then the process of development, printing, again changes the color a little bit. Then it aged, it got scanned, and all these processes changes the color a little bit. And to make this point, here we have the same picture from a different Wikipedia user, and it's the same source picture, but we see that the colors are notably different. And this is the problem with photographic reference. So what about we are lucky enough to have the aircraft we want to model in a museum nearby? Now first, is it still in the original color? Maybe, probably not. If it's still in the original color, the color aged a lot. This aircraft is probably 80 something years old by now, and colors age a lot. And when colors age, they change their color. So, what does it bring us with reference for our models? And if you ask me, it's a really freeing thought, because color accuracy doesn't really exist, and so if you build a model for yourself, it's very simple. You choose which color you take, and no matter what you choose, it's the right choice. Very freeing thought, if you ask me. If you build a model for a client, it's of course the choice of the client, and if you have to color match it because you work in the film industry and you have a model and the original, yeah, then you are a little bit in a pickle. But the good thing is, today with digital technology, we usually do the color matching in post, because in the computer it's a lot easier. And that it's an incredibly difficult task you see on old VFX films where digital technology wasn't there at the time, and you often see a distinct color change between the model and the original. And even with all the skills I had, it's an incredibly difficult task. Now, the interesting question is, of course, how do we deal with this in printing, where color accuracy is a big deal? Now, today, usually files come in a digital form, and what we can apply to them are color profiles. So that is very simplified, just a table that says, if this color is in the digital file, we use this settings for our printing machine to reproduce said color. There are a lot of other variables in it, but for this, go to university and study printing technology. It's way too much for a YouTube video. So that's it, and then we can print it. And for day-to-day printing, it's good enough. What if we need a little bit more accuracy, because we have a cola bottle printed in factory A in March, and here we have a cola bottle printed in factory B in August, and at the retailer, when they are standing side by side, the color should be exactly the same. Now with this, we solve this problem with spot colors. Probably the famous system of this are Pantone colors. So we as a printer, we can order them ready mixed, and then just simply apply them to the paper. Just simply is a very big oversimplification of things, but as we don't have to mix the color with the CMYK process, we have much higher color accuracy than otherwise. So that's basically it for this episode. A little bit different than the usual stuff, but I hope you enjoyed it nonetheless. And if you have questions, comments, as always, let them down below, and I try to answer them as quickly and correctly as possible. And all that's left to say now is thanks for watching, and see you the next time. Bye bye.